This last video is about the concept of augmented matrices. And to look at that concept, I don't want to write in red. I'm going to look at a linear system we have seen before, a very simple one in two space. Okay. And essentially here, we have named the variables x and y, right? But I could have renamed the variables, x1 and x2, and it's basically the same linear system, right? I'm just renaming stuff, right? So the important thing in that system are the coefficients that we that are there. That's important in order to recover the solution set. The names of the variables, well, if I change the variables, well, I mean, if you've got the solution set for a system with other names for the variables, it's very easy just to change everything and change the labeling of the variables, and then you get the other solution set. But if I change the constant, it's going to change the solution set completely. So if you do some work to get the solution set, you're going to have to redo all that work. So just to say that the important part in this system are the coefficients in front of x, y, and also the constant is important. So here I've got two constants. So we're going to put these numbers that are the ones that are truly important in an array like that, and we're going to put sometimes a little dotted line just to specify that this last column, it corresponds to the constants in my linear system. So this object that I've created, an array of numbers, we're going to call that a matrix in this course. Now, here I've got a matrix that's related to my linear system. Sometimes I will have matrices, that's the plural of matrix, matrices that are completely unrelated to the linear system. They just stand on their own. So it's not because you have got a matrix that it's associated to a linear system. But right now it is. Okay, partly actually, I guess, because you've got the matrix of coefficients, the ones that that multiply the variables, and if we add to that matrix the constants as well, so the column of constants, we get what we call an augmented matrix. So the augmented matrix includes all the information that's relevant to my system. Okay, so now what I'm going to do is change the linear system, and through this we'll see how I can change the augmented matrix similarly. I also want to no, I'll do that in the end. I want to look at geometrically how these equations look like, but I'll do that at the very end. So what can we do with a linear system? Okay, these are things we've done so far. We can multiply an equation by a non-zero constant. I can multiply an equation throughout by a non-zero constant. For instance, I could take the second equation and multiply it throughout by 2. And I get this. It's not changing the equation. And if you think about the graph represented by that second equation, it's not changing. That graph stays the same. It's the same set of points that are part of this equation that are part of that satisfy this equation. So this is not changing the solution set of my system if I do this. In my augmented matrix, that's equivalent to multiplying the second row of the matrix by 2. So multiplying every number here by 2. So as you see, I still have the coefficients, right? Those are the exact same coefficients here. So I'm changing my system, I'm changing my augmented matrix. Why is it a non-zero constant? It's because if I multiply throughout by 0, I'm just going to, right, if let's say I do this, I'm going to get 0x plus 0y equals to 0. So this is meaningless in the sense that all xy are solutions to that. Like, so that this is basically like erasing the second equation. It would be just like removing this completely, and I want to do that. I want to keep, if I remove it, it's going to change the solution set. But if I multiply it by a non-zero constant, it's not changing anything. The solution set stays the same because the solution set of that equation stays the same. So to say that we have multiplied equation 2 by 2, I will write next to my augmented matrix that the second row, so R2, R is for row, second row has been multiplied by 2. What else could I do? I can subtract or add an equation to another equation. We've done this before. For instance, what could I do? I could subtract, like I could do equation 2 minus equation 1. Well, maybe this is 1 and 2. If I do equation 2 minus equation 1, and essentially the 2x and the 2x will cancel out. So I'm just going to recopy the first equation. But in my second equation, the variable x is going to disappear because 2x minus 2x is 0x. And 2 minus 2y minus y will give me minus 3y. Minus 2 minus 4 will give me minus 6. So I can do that, and you can try to convince yourself it's not going to change the solution set, in the sense that I could always come back to the previous system by adding equation 1 again, and then I'll be back to the previous system that I had. So I haven't changed anything here. In terms of my augmented matrix, I would say I've taken row 2, previous row 2, and I subtracted the previous row 1. So when I write row 2, row 1, they're always referring to the rows of the previous matrix, not of the current matrix. If I do this, they change to 0, minus 3, and minus 6. And I can keep going. What else could I do? I could solve for y. So to solve for y, I would divide by minus 3. So I would take row 2 and divide by minus 3, or if you prefer, multiply by minus a third. I would get 1, 0, 1, 2. In terms of an equation, I would get y is equal to 2. I could also do the same for, well, kind of the same for x, in the sense that I could try to remove the 2 in front of the x here. To do that, I would do 1/2 of R1, right? R1 being the row that's previously written. That's written in the previous matrix. So 1, 1/2, and 2 would be the new row of my augmented matrix. And that would, so this is essentially doing, well, what did we do? We divide everything by 2 here. So x plus 1/2 of y is equal to 2. And finally, I can kind of do the two operations that I did before, like multiply by a constant, a row, and subtract an equation from another equation. I can do those two steps at the same time. I can add and subtract, or subtract, add or subtract a multiple of an equation to another equation. So that's kind of doing the previous two steps at once. So for instance, I could say, okay, I'm going to do row 1, I'm going to subtract. So row 1, I'm taking row 1 here, and I'm going to subtract 1/2 of row 2, 1/2 of that row 2. So if I do this, okay, 1 minus 1/2 of 0 is 1. 1/2 minus 1/2 of 1 is 0. 2 minus 1/2 of 2 is 2 minus 1, so 1. And I have even changed the second equation. So what have I done here? Essentially, let's look at the corresponding system. Now it's written x equals 1, y equals 2. By doing this, I get a linear system that's super easy, right? It gives me right away the solution. So those steps that I've done, it has made my life a lot simpler in terms of recovering the solution set. I got a system in the end that was much simpler than the one I had initially. I get for free, right? I get without any effort now. The solution set is the single point, so it's one solution. It's 1, 2. So now that we've done this, let's take a look algebraically at what we've done. So initially we had this linear system. It's the intersection of two lines, right? One line is the line 2x plus y equals 4. So that's a line going through 2, 4 like that. 2, 4. And x minus y equals minus 1. It goes through 1 and minus 1 and 1 here. So like that. So our solution set is here. Okay, so that's not going to change. You'll see the lines are going to change, but the solution set's not going to change. It's always going to be, so this is 1, 2 here. And let's see that this is not changing. So while I'm working with my equation, so after that, what did I do? Yes, I multiplied the second one by 2. So that's not changing the equation. So I still get the exact same lines here. So nothing has changed at this step. After that, what did I do? I subtracted an equation 1 from equation 2. So of course my lines are changing here. So the second equation, well, the first equation isn't changing. It's still like that. But I don't know what's going on here. Okay, but the second equation has changed. Now it's y equals to 2, or minus 3y equals to minus 6, but it's the exact same thing. So now it's just like that. This is y equals to 2. Okay, this one hasn't changed, right? It's still this. And I still get the intersection point 1, 2. Hasn't changed. And in my last step, what do I have now? I've got x equals 1, y equals 2. So that now the first equation is changing. It becomes straight like that. X equals 1, y is 2. And bingo, I've got the intersection point. So even graphically, I can see that I can easily recover the solution set from these two lines. These two lines are now perpendicular. So by doing these, what we call row operations, it's operations on the rows of the augmented matrix, our goal is essentially to get a linear system that's a lot easier to solve. And graphically, it's basically coming up with planes or lines that ultimately are perpendicular to one another.